Awesome. Welcome, everyone. Thank you for joining us. This is the Microelectronics and Semiconductor Showcase with Tech Showcase, and we're gonna get started now. For today's agenda, today's showcase is a little bit different than previous showcases we've had. And if some of you are repeat attendees, like Han here, I know has been to a few, Robert as well. A lot of familiar faces in the crowd. For those who aren't so familiar, this showcase is going to be super focused, as opposed to the usual format where there's an open topic in the very beginning and that followed by the industry topics. Today, we only have one session, and the session is focused specifically on semiconductors and microelectronics. So you're in for a very specific ride. So the vision of Deep Tech Showcase, just so everyone knows, has an idea of why we're doing it. There's a few reasons why we're doing it, but the easiest and most I guess philanthropic one that we could talk about today is to bring tech to market through community, through ecosystems. So basically, it's allowing us to take a look at emerging technologies and say, hey, that looks really cool. Why aren't we using it, or why aren't we talking about this more, and bringing them a stage, bringing them a platform in which they can speak. Which has been, we've had some partnerships occur through this. We've had a lot of different chain reactions through these events. So it's really good that everyone's sticking with it. And on top of that, we're getting new companies to present every single time. So it's really a really fantastic event, and get ready for it. So the ecosystem contains startups, tech scouts, and investors. The tech scouts could be both federal as well as corporate. Within this ecosystem, and how we really focus it is we have events like this one where we focus on a specific industry. So this one's microelectronics and semiconductors, and in the future it's going to be I'm just going to jump ahead a little bit. The next one's aerospace and defense, so stay tuned for that. That one's going to be probably quite a bit larger, and then after that we're going to have an advanced materials event. But between the events, we also reach out and usually send company profiles around with the goal of gaining traction without necessarily just the events, but also doing a little bit of matchmaking on our own. So if anyone here is on this call and says, hey, I would love to see deal flow from XYZ, some kind of deep tech, we're happy to try to set you up and try to send it your way. And that's basically Deep Tech Showcase in a quick nutshell in less than 4 minutes. It's the events, the guided introductions, and trying to enable and leverage connections as well as different sources in order to help emerging technologies really come out to play. Now, I'm happy to introduce my colleague, Benjamin Sampson. He's going to talk a little bit about our sister company, Eagle Point Funding. Benjamin, the floor is yours.
My pleasure. Thank you so much, Asher. So Eagle Point Funding is a grant consulting and a grant writing firm. What we do is we're focused on accessing the non-dilutive R&D funding that is being given out by the U.S. federal government. So whether it's SBIRs, STTRs, broad agency announcements, OTAs, if there is funding out there for either companies in your portfolio or you yourself, we're going to work with you to go ahead and access that funding. Now, we do 3 things for you, and it's in conjunction with the Tech Showcase. The first is we're going to handle all the identification of the grants. We're not going to make you go ahead and find the stuff. We're going to go ahead and find it. Number 2 is we want to handle the vast majority of the work. We want to handle budgeting, technical documents, business proposals, formatting, editing, writing, laying it out, submitting to the agencies, communicating with the agencies, essentially whatever a client will let us take off their plate, we will. So they can go ahead and focus on their R&D, not have to worry about anything else. Now, why we've risen to this place, to really the top of this industry, it comes down to 3 things. The first is we know and understand the federal funding system. We've been in this game for about 24, going on 25 years, and we've submitted literally thousands of proposals. And so we understand these agencies, we understand what they're looking for. We've got connections with program officers and people all the way from the reviewers to the heads of the departments. We've got connections to help our clients win and be put in front of the people who are going to make a difference in the success of their grants. Number 2 is we really don't look to work with companies for a grant or 2. We're traditionally working with clients for 18 months, applying to somewhere between 15 to 20 grants during that time. We don't have a cap though, so we'll help clients go for 25, 30, 35. It's just a matter of how much they're interested in applying to. And then lastly is really we tell the story of the technology, because we realized pretty early on that These reviewers, they're your peers. They understand the technology. They're going to understand the technical side. What they need to understand is what is the vision? What is the dream? How is the tech that you're proposing really going to change the status quo and change the market when it's developed in a year, year and a half, 2 years down the line? And so we found that the more that we could put that, illustrate that and outline that for the reviewers, the better success we had with clients. So to work with us, as I said, it's 18 months. You're going to get somewhere between 15 to 20 grants. Our business model is very simple. It's a consulting fee and a success fee. The consulting fee is 6 quarterly payments of $21,000 for a total of $126,000. And we also take a 5% success fee on any of the grants that we help a client win. Now, I will say we do also offer a guarantee to our services, and the guarantee is that if a client works with us for 18 months, sticks with the program, doesn't leave early, we guarantee a client is going to walk away with at least $1 million in funding. The reality is most of our clients are walking away with about 1.2, 1.5 on average, but we guarantee at least $1 million in funding to be won by a client. But obviously, if you want to talk, if you want to hear a little bit more about this, I highly recommend you scan the QR code, book some time with me, or ask Asher. He'll be happy to set up a meeting. Asher, this is your show. Take it away.
And with that, we're going to quickly go over the agenda. Right now, we are in the midst of the opening presentation and meet the panel. First up, we are going to have Accelerium present. After that, Jiva, followed by Quantum Transistors. After that, Dot Factory. And finishing up, we have Neologic. And now we are going to introduce the panel. What I'd like to have is, if each, as I say your name, if you would mind introducing yourself and kind of giving some background, just so that the presenting companies could have a better idea of how to shape it, and two, give a little bit of background for everyone in the audience. So without further ado, let's start with the beginning of the list. Jonathan, you want to quickly introduce yourself?
Sure. Hi, Jonathan here. So from ITIC, which is the venture arm of ITRI, which is one of the largest research organization over Taiwan. We're funded in 1979 due to E3 doesn't hold equity. So we're funded at the time, and we help nurture a company like TSMC, UMC, all these semiconductor companies back then, 30, 40 years ago, and switch focus to mostly display area in the 2000s era. And now we are really just acting like an independent VC, still stay synergy with E3, but also look at other deals as well.
Perfect. Thank you for joining. That's fantastic. Next up, we're going to skip over to Rajesh. Rajesh, you want to quickly introduce yourself?
Hi, Asher. Could you come to me at the last? I'm just finishing up on the call. I'm sorry.
Absolutely. No, not a problem. Mike, you want to go ahead?
Hey, this is Mike Freeman. I'm with Innosphere Ventures. We're a combined 501c3 science and technology incubator working predominantly in the Mountain and Midwest states in the U.S. and also a financial investor VC.
Perfect. Thanks, Mike. Next up, Andrew.
Hi, everyone. Andy with Micron Ventures, the venture arm of the memory giant Micron Technologies. Love investing in early stage semiconductor companies and helping awesome founders fight and win.
Nice. Awesome. Thank you. Robert, you're up.
Yep. So Robert Evan, M Ventures, the CVC of Merck of Germany, looking at early stage electronics deals around seed A round.
Perfect. Yuan, you want to quickly introduce yourself? You're muted, I think.
Yeah, hi, I'm Yuan from Hypertherm Ventures. We are the venture arm of Hypertherm. So we are a global leader in industrial cutting, and we're always curious to learn more about any like the tech applications for industrials.
Perfect. Thank you for joining. And last but not least, we have Han. Han, you're up.
Yes, thank you. Hey, this is Han Ko. It's always a pleasure to be with Deep Tech Show. Been here many times, been always a pleasure. Always there's something new I can learn, and that's a great venue. Also, especially the topic today, semiconductor, I'm pretty excited. About my company real quick, USACO Group. We're an international venture capital company. We invest in companies from of course, US domestically to all the way to European and Asian. We invest up to Series A or B, and we have a particular interest in semiconductor, as well as AI and robotics and some blockchain. Looking forward to working with you. Thank you.
Perfect, perfect. And I accidentally skipped Jasmine. You want to quickly introduce yourself? Sorry about that.
Don't worry at all. Hello, everybody. Great pleasure to be here today. And I'm Jasmine Zhang, Investment Director from SK Hynix America. And yeah, we're based in Silicon Valley, and we're interested in any type of technology that related to semiconductor. And being at the so a few familiar faces. Very pleased to be here today. Thank you.
Absolutely. Thank you for being here. Perfect. So with the introductions done, Nasser, it's I believe that you're up first. Feel free to start sharing when you're ready, and we'll get started.
Can you enable me to share?
Yeah, sorry, that's on my end. Okay, you should be good now.
All right. Let me know when you guys see the screen.
We see the overall. Yep, it's full screen now. It's perfect.
Perfect. Thank you guys for taking the time. I'm going to talk about Accelerium, which is a fabless semiconductor doing reconfigurable compute for the convergence of sense and communication. If you take a look at what's really happening, at the end, you see that there is a big convergence, and between RF sensing, computer vision, wireless, and AI machine learning. You see the bandwidth is going from 1 gigahertz to 10 gigahertz. Lots of need for more bandwidth. 5G and 6G is coming. You need a wider bandwidth to handle higher speed. You see complex workloads. AI, sensor processing, being able to process a wide bandwidth from that perspective. But also you need to do that with low processing latency. For example, spectrum sensing, you can't just take your time to process this. And with all that, you need a low C-swap. From that perspective, there's quite a bit of thermal and form factor limitation, size and power. So that's actually create a challenging environment from that perspective. And at the Accelerium, when we looked at the conventional computing architectures, you can go with ASICs, but these in general have limited flexibility. It will cost you, it depends on technology, between $50 million to $100 million to develop. It might take you about 3 years time to market. And it has a limited product life because, if anything changes, especially, the algorithm or the AI machine learning or, the standards are really changing, you're going to spend that silicon. On the other hand, many people are actually doing FPGAs for many of these applications. These are really big, high power, difficult to program. And in general, for many of these applications, it's really slow for a reconfiguration time. So if you configure it for a certain application and that's it, you don't really need any flexibility to switch, then it might be okay, but you still have to worry about the size, the power, the form factor. So it limits its use in many applications. Of course, people use GPU in some of these areas, but it has high latency, also high unit cost and power from that perspective. So there is a need for a new architecture that provides an ASIC cost with power and performance. And that's where Accelerium comes in. We actually are the only developer of a reconfigurable compute that provide you an ASIC C-swap, but with a full flexibility, of an FPGA for a domain-specific, basically applications in the communication and RF sensing from that perspective. We provide almost a 50x lower power than GPUs. Our products actually more than 50x over any standard vector processor from that perspective. It's a million times faster reconfigurability than FPGAs. And it includes specialized instruction for DSP and AI machine learning. So it's a platform that's optimized for RF sensing, communication, and inline AI. Our first, product chip, it will be the XLR 1000, and it's a reconfigurable compute platform. It's versatile. It can handle, wireless infrastructure, advanced radar, phase radar, high performance compute and AI and machine learning and more. It supports, the different, basically integer 8, even 2 and 4, especially for inferencing for AI and machine learning. It does floating point complex operations. It's actually scalable from 4 TOPS to 1,000 plus TOPS. It's homogeneous, so it provides resiliency. All these edge processing units are similar, so you can move code around from that perspective, and you can scale. Or C programmable, so you don't have to deal with an FPGA code, and it's all ISA compliant. So you actually use off-the-shelf, basically tuning from that perspective. So you use your familiar tuning perspective, GNU, GCC compilers. It supports streaming and vector and matrix operations, which we think is a novel patented architecture. So it depends on the workload. It actually adapts its microarchitecture to the software. So if we're actually doing matrix multiplication, our compute configure itself systolic to give you a huge boost in performance. If you're actually doing and sitting next to an A to D and D to A, it works in a streaming mode to enable a very low latency. How if you're doing any of the signal processing, it configures itself vector processor. So actually, we have an architecture where it adapts itself to the software rather than the other way around, where you actually try to get your software to fit into the hardware from that perspective. It provides an ASIC performance, with full programmability, with C programmability, pushing all this all the way to the samples from the ADC and DAX. Okay, sorry, I went backwards. But just to give you some examples of where this would be used in the applications, joint communication and sensing for autonomous driving, UAVs and drones. Conventional approaches you will need to do, usually it's based on analog FMC waveforms with custom radar processors. And in order for you to do communication, you actually are going to have a different, basically modem to do that. With our platform, which is the only joint communication and sensing platform, you only need our compute fabric with the ADCs and DACs. Enables you to do advanced waveforms. It will enable you to do advanced signal processor techniques that we have, which actually reduce number of antennas, almost 4x reduction in antennas for compared to existing solutions. It provides also in-band gigabits per sample data link, so it provides you V2X, with a gigabits per second bandwidth, so to allow cars or drones or robots to share data. It's also all C programmable, so it's in-field upgradable. It's secure. It implements security and interference resistance. And again, it has advanced DSP and AI machine learning algorithms implementation with that.
30-second warning.
Sorry?
30-second warning.
Oh, okay. So other areas where we're actually getting traction is into basically 5G wireless infrastructure, as well in aerospace and defense for phased array radars and 5G MIMO, as well as an L1 acceleration. There are many applications from that perspective. Where we are, we established in 2020, we have an FPGA. We're taping out a test chip in August. We already have a customer for a $4 million contract with a customer. We already have an MOU with the Department of Air Force and Defense. In 2023, we're going to tape out the chip as I indicated. We're going to do demos. We want to sign up our second commercial customer. And we're actually in track and writing a contract now with the US government for more than $3 million contract right now. We're in negotiation with a contract with the US government. And in 2024, we will actually tape out our chip, the production chip. So where we are, so what we're actually still have a seed round open, but we're looking for Series A, $10 million to tape out our XLR 1000. What we're looking for is letter of support and MOUs for the US government, but also we're looking for corporate partnership for the production silicon and joint development. And we also licensing our IP, from that perspective for adjacent market segments. So if there's an interest for high performance reconfigurable compute as an IP, that goes into many areas and applications. We're interested in that. Team, we're about 25 people. We're actually came from Intel, Broadcom, and we have a great team with great expertise from top-notch schools like Stanford, UCLA, Georgia Tech, and have across the spectrum from a experience perspective. we have done quite a bit. And Rahil, the founder, actually was the key lead on all the modem development for Qualcomm chipsets, 3G, 4G, 5G. And myself, I was a senior VP GM of, basically at Mindspeed, where we're actually leader in 3G, 4G base stations, and I was a GM at Intel. With that, thank you guys, and really appreciate it.
Absolutely. Thank you. Thank you so much, Nasser. So what we'll do is like previous showcases, let's raise our hands and we'll get to the questions in order of hands raised. So feel free to begin. Okay, Andrew, you're up.
Yeah. Hi, Andy with Micron. So this is it's a pretty crowded category that you're entering in with lots of bodies over the last couple of years. I guess like as you look at that and appreciate that, like what lessons have you learned from the startups that have come before you, like going after this like edge AI compute, universe? Like what I'm interested in, like what learnings have you observed from the community?
Oh yeah, I mean, yes, I mean, and that's why we said we're domain specific. So we're focusing on RF sensing and communication. We're not looking for the general category of edge computing from that perspective. So as you can see, we have customers, they will be building 5G and then moving into 6G from that perspective. So we're actually moving the compute and the intelligence into the sensors themselves, be it on radars for the cars, in aerospace and defense for phase array, for warfare, and where you actually need to sense the spectrum and do communication. So we're focusing on communication out of sensing and the convergence of this where 6G is going to be coming from that perspective. So we're actually domain specific, and that's why we have specialized instruction for digital signal processing and AI machine learning from that perspective. We actually can do 20x than any DSP out there from a performance perspective. So we're actually focused on pushing the intelligence, the sensors, and focus on domain specific general category from that perspective.
Got it. Thanks.
Perfect. Han, you're up. You're muted though.
I'm sorry. Yeah. Hey, thank you. Great presentation, and I like your actually product there. Just a quick question here. So just two quick questions here. So
Sure.
First of all, your intellectual property, you got it secured on global, I guess, suppose, correct?
Sorry?
Your intellectual property, you have a
Yes.
file patent. Oh, in global. Right?
Yes,
Okay.
we have patents and we have trade secrets.
Okay. Right, both. Okay, got it. And you're a US-based company or?
Yes, we are a US-based company. We're out of Irvine in Southern California, Orange County.
Okay, got you. If you are to work with some fund or companies collaborate in an overseas, are you bound to ITAR compliance or not?
No, it's our products. It's dual purpose. And again, our discussion with the contract where we'll just stay on the commercial side. We provide them with the commercial references, and they actually have right now 3 primes going to be working on our technology, and they will handle all the secret stuff. So this is commercial, but it has a dual use into the US government.
Got you. Okay, right. Thank you. Appreciate it.
Perfect. Mike, you have the last question.
Nice presentation. I wasn't really clear on from an application and market perspective how big these markets are as you see them. You went
Sure.
through pretty quickly the applications. Can you just speak to that just generally?
Yeah, sure. I mean, the wireless infrastructure is in the billions of dollars at the DU and the RU. For example, the aerospace and defense, if you look at Xilinx from an FPGA perspective, just to address that market, Xilinx themselves, they generate more than $1 billion from aerospace and defense and FPGA. This can be great FPGA replacement for communication, for software-defined radio, for phase array, antennas, and for electronic warfare, where you actually want dual modality, where you actually can do communication as well as spectrum sensing and AI machine learning within the same product. So if you take a look at Xilinx Versal, they try to build an SoC which is heterogeneous. In our products, all C, ISO compliant, can do what Versal is doing, but at 1/100th of the size and at 1/20th of the power.
information is on the screen, but feel free to leave it in the chat because we're about to move on to the next presentation. So feel free to leave it in the chat, and yeah, feel free to connect with Nasser. Next
Thank you,
up
guys.
we have absolutely. Next up we have Jiva Wireless. The floor is yours. Feel free to get started. I see you already shared your screen, so feel free to get started when you're ready.
Hey y'all, everyone hearing me okay?
Yep, loud and clear.
Thanks so much, Asher. I'm Aaron Parks, CEO of Jiva. We're located right here in downtown Seattle, Washington. So Jiva is providing an entirely new tool in the arsenal of hardware engineers and product designers. This is a new way of communicating wirelessly at extremely low power. So whether it's an Apple Pencil talking to an iPad, a wireless home security system, a vibration sensor predicting equipment failures, or a temperature tracker on a pallet, there's a common pain point shared by all users of wireless sensor technologies, and that is the size, cost, and hassle of batteries and battery replacement. So what's the main problem here? Radios consume a lot of power. 85 to 95% of a typical wireless sensor node or peripheral device's battery just goes to moving the data across the wireless link. So conventional systems can have either long battery life or they can move lots of data, but they can't really do both. So you can think about this sort of trade-off curve between these two things, moving lots of data and getting a long battery life. We've placed some conventional technologies on this curve. We've also placed some potential disruptors on this curve. Getting over this trade-off line and being able to move more data for less power is kind of an uncharted opportunity. And that's actually where Jiva Tech operates. So how do we do that? How do we claim to do this here? So conventional radio is a bit like a flashlight. You take energy from a battery, you convert it to a radio signal, you modulate it with information, and you push that energy out into the environment. This is power intensive, it's complex, it's expensive to do, but there's actually another way to communicate, which is backscatter. So with backscatter, you reflect energy to communicate. It's kind of like a signal mirror. And this is what Jiva Tech actually does. So with this technique, you can move more data for less power. And because of reduced complexity, you can get down to reduced silicon area requirements and reduced battery requirements. Collectively, that results in essentially cheaper and smaller devices at scale. So to make backscatter work, you actually do need to have some type of base station or access point that supports it. That base station will send out an illumination signal, which the backscatter device is going to reflect. So there's no free lunch here. What you're doing is moving the power and complexity of generating a radio signal away from that low power device and to the base station side. But Jiva's secret sauce is that we transmit conventional protocols using backscatter. So we're using this technique of, generating radio signals using reflection or essentially communicating through reflection, but we are doing that and still talking Bluetooth, Wi-Fi, and LoRa. So this means we can be intercompatible with commodity wireless chipsets that are already part of existing product ecosystems and infrastructure, but we can get the benefits of backscatter communication. So this is what an implementation would look like in a consumer device. We can actually temporarily repurpose 2 of the many existing radios in the device to act as transmitter and receiver. And now this phone, in this case, can talk to an ultra low power backscatter device using Bluetooth or Wi-Fi backscatter. So the battery life and power requirements of something like a stylus are almost entirely driven by wireless connectivity. So this can have a huge impact. So more data for less power is what we uniquely offer today. And really, this is the tip of the iceberg. Ultimately, Jiva's unique tech is the only way to get the power, cost, and size of a device down to something like an RFID sticker, while also maintaining the performance and interoperability characteristics of conventional radio, like long range and ability to work with existing devices and infrastructure. So saving all this power and communications also dramatically lowers the hurdle to get to battery-free devices a short ways down the road, which have maintain some high levels of capability, essentially. So with that, Jiva is at a really interesting inflection point right now. We've crossed many of the engineering hurdles needed to unlock the benefits of our tech. I think like many deep tech startups over the past few years, especially, our path has not always been smooth sailing. But we fought our way through and we've come really close to some really big wins. Right now, we're midway through a pivot. And once we've validated our new direction, we expect to be raising funds to move forward. We're looking at moving into a vertical play around machine health monitoring using our unique technology to drive some unique benefits in that space. So we're kind of seeking investors right now who are up for some early conversations with us to understand how we could work together a short ways down the road. We're also looking for partners who can work alongside with us and whom we can work alongside to find some amazing opportunities for deploying this unique tech. So would love to follow up with any of you, and I'll be happy to take questions now.
That was fast. Go right ahead.
Oh, hi, Aaron. Thank you, Arthur. Hi, Aaron. I have a question regarding the working principle. You have mentioned that it is illumination of signals. Does it enhancing the signal during data transmission? And also, I'd like to understand, the distance limitations for the signal range.
Jasmine, I caught the last half of your question, but your audio is
Oh,
cutting out a little bit in the first
sorry.
half. It's about distance.
Maybe I'd like to understand more about the signal range.
Yes, absolutely. Yeah, so let me bring up this slide, which talks a little bit more about how we actually implement this. So getting down into the nitty gritty a little bit, there's actually two different ways to implement Jiva backscatter today. The first is to apply a Jiva firmware stack to existing, for instance, Bluetooth low energy SoC that enables this sort of software defined backscatter mode that in fact can save you about 90% of the communications power consumption. The connected range of a Bluetooth backscatter system is just about 5 meters. So it is reduced over a conventional Bluetooth system, but it still enables some, personal area network applications and some sort of device peripheral communication. The second way to do this is to bring our Parser backscatter modem IC into a design. This can save even more power, and it can actually get you to longer range because it unlocks protocols like LoRa, which because of the dramatically improved sensitivity, actually lets you get to about 50 meters operating range for an ultra low power device. And that is at about 100 microwatts power consumption. So I hope that answers your question a little bit about range.
Thank you. And my first question is about the working mechanism. So during the transmission of the signal, is there any enhancement technique, during the transmission of the data?
Enhancement technique?
Yeah.
Yeah, so essentially the device is generating a packet in a standard compliant format, but it's doing it rather than using a local oscillator and a mixer and mixing with a modulated baseband signal. It's essentially it's crafting that same waveform, but it's doing it by reflecting energy. So we're applying a specially crafted signal to a unique type of impedance modulator that's connected to the antenna. And all of that is protected with patents and things. So that is how we actually are able to generate that standard signal using a backscatter technique.
Right. So I'm sort of understanding, I'm sorry, maybe too many questions, but this is going to be my final question. I promise this. And so for the distance range, if it is 5 meters, I can understand. What about 50 meters? You can also allow 50 meters distance. And while data transmitting, is there any going to be interruption from the environment? How are you going to deal with that?
Yeah, great question. So the distance sort of question really is related to the underlying protocol that we use. So for instance, when we are talking Bluetooth, we get about 5 meters range. And when we're talking LoRa or some other protocols that enable a much improved receive sensitivity, we can get up to that 50 meters range. So it's really application dependent in the sense that, if you have a particular application requirement around range, around data rate, we can basically see if backscatter is a fit for that by evaluating how that underlying protocol will what it will enable in terms of throughput as well as range. But the interesting thing about our underlying tech is that it is at its core, it's protocol and frequency agnostic. So backscatter can actually be applied to any protocol in any frequency band. So you can imagine, making use of this all over the place in various applications.
Thank you, Aaron.
For sure.
Thank you, Asher.
Perfect. Thank you, Jasmine. Mike, you're up.
Hey, Aaron, how have you funded this, the technology development to date? And I wasn't really clear on what you're looking for. You were a bit vague on,
Yeah.
some partners and maybe some money. Could you be a little more specific?
Yeah, absolutely. So I think I mentioned we're, firstly to kind of describe how we funded it to date. We do have some VC and angel investment that's occurred over the years, totaling about $5 million. We've also had about $2 million in SBIR funding over the years, and we've also had again about $2 million of essentially, customer-driven projects, NRE and evaluation work that we've done with customers, leading now into some early-stage product sales, but very minimal on the sales side, more focused on this sort of NRE engineering evaluation, understanding how this fits into a product ecosystem. So that's kind of how this has been funded thus far. And then in terms of what we're looking for right now, we are right in the midst of executing on a pivot. So we're trying to figure out whether the path that our team has outlined for moving forward is the right path. We're trying to take some early market validation steps and really go back to the fundamentals of what makes a really good business. I think one of the challenges of a deep tech startup coming at this with a unique and interesting technology is figuring out exactly where and how to apply that. And, we have struggled with that in the past. And I think that is something we need to place front and center right now. So right now we're midway through some market validation of a vertical play around machine health monitoring using this technology. So high bandwidth machine health sensors that use this technology to achieve long battery life and high capabilities at the same time. And so what I'm looking for right now is really just some early conversations. I'm not ready to raise quite yet, but we're looking for some early conversations to kind of get a relationship started and understand how we could move forward together a little ways down the road.
Perfect. All right, Han, you're next, and then Robert.
Sure. I really liked your technology. I know this the radio ID tag was only available for like tracking boxes, right? But now you actually apply to. I'm just curious. So what frequency you guys operate? What megahertz?
Yeah, great question. So we have a BLE solution that does operate at 2.4 gigahertz. And then we have today also our Parsair integrated circuit here on the right-hand side of this slide. That is a 900 megahertz band, so 850 to 950 megahertz approximately, worldwide band operation. But the underlying technique is protocol and frequency agnostic, so we can actually operate at any frequency band, and our IP covers, operation in any frequency band.
Gotcha. Now about the quick business question. So how long you been in business, and do you have any traction? Have you generated revenue?
We have. So we have about $2 million to date primarily in revenue from NRE and evaluation type of projects where we've actually done some early stage pilots with, we've done a fairly advanced actually pilot with a consumer electronics company. We did an early stage pilot with a major retailer monitoring goods as they move through the supply chain. We've worked with consumer packaged goods companies. We've actually worked with building materials manufacturers to incorporate sensors into building materials. So these are all very, very interesting pathways, but all of these were early stage evaluation, pilot scale projects that as you can probably sense, didn't pan out in the way that we had hoped. And so we're right now kind of reevaluating our path forward and figuring out where to go next.
You have a great potential. How long you been in business? How many years?
Oh, yeah, absolutely. So we kicked things off in about 2016. So we're a spin out from the University of Washington here in Seattle. Spun this technology at the university in about 2016. Yeah.
Gotcha. Maybe we can talk offline a little bit later. Thank you.
Would love to. Thank you.
Perfect. Robert, you're up.
Yeah, you partially answered my question. I want to know more about the use cases. Like you gave some examples here where you did some trials. Where do you think there's the real value where you can really deliver that, with your extra range and power consumption, that you can really make a difference?
Yeah, absolutely. I think there's a short-term answer to that question, then there's a longer-term answer to the question. And the immediate term one is the one I'm focused on right now, which is how do we get to something really interesting right away. Today, we can uniquely offer more data for less power. So that means basically moving a lot of data. If you think about applications where you want to stream a large amount of information and you want to do that in a wireless way. So for instance, the flight test instrumentation is a great application where there's a lot of data being moved. I'm also very excited and gung-ho about like machine health monitoring systems. So imagine a peel and stick sensor that can stream full bandwidth vibration data, even acoustic data from production equipment on the factory floor, giving you a lot more information to feed into your AI analytics system for purposes of detecting and predicting machine failures and alterations in essentially in things that affect productivity and downtime on the factory floor. So I think those are some areas where near term, very exciting, long term, requiring multiple kind of iterations of the technology and building on this base platform. I think we can get to applications where we have devices that can resemble RFID tags, but can talk Bluetooth to a phone, or essentially get down to the price and performance parameters of RFID, but maintain the ability to do sensing and things like that. So I think there's a long-term opportunity in that, but of course that requires massive scale to get there.
Okay, thank you.
Perfect. Thank you so much, Aaron. Feel free to leave your contact info in the chat when you're ready. And thank you for the presentation. Next up, we have quantum transistors.
Hi guys, can you hear me?
Loud and clear.
Great. Good evening, everybody from Tel Aviv. Thank you for taking the time today to join us. The subject I'm going to expose here today is probably much bigger than I can do in 10 minutes, but I'll do my best to give you the gist of it, and anybody who wants more details is welcome to contact me later. So Quantum Transistor is a very young startup. We've been, since our seed funding, it's been 5 months. And we are building a universal single chip quantum processor. To basically state the idea is we're trying to build the 8086 of the quantum world. Okay. Doesn't move. Oh, there it is. Okay. So I'm not going to spend too much time telling you how important quantum computing is going to be to our future. But I think in 10 years, it's probably going to have an impact on each and every one of our lives in multiple different ways, in multiple different verticals. But this is a lot of hopes, a lot of aspirations, and this is the reality today. Really big machines that we think are going to be between 1 and 2 years to get to minimum viable product that goes to enterprise and can actually start making some truth out of those promises. And those big machines are going to be very expensive, very power hungry, and they're going to be very similar to where classical computing was when we all pulled out cards and fixed them and all that kind of stuff. So this guy and this guy really are in the same place in terms of evolution. The vision for quantum transistors is basically building a chip that looks like a GPU or looks like any other coprocessor that has the quantum computing engine all inside of it, has a host interface, and can function within a hybrid system in the same way that you're used to using a GPU today. Okay, that chip obviously will not be able to be cooled to 15 millikelvins, otherwise it would have a huge refrigerator stuck up behind it. So our technology is available from 4 Kelvin to room temperature. We've actually done initial testing in room temperature, but we're not going to be taking the risk of putting a product to market in room temperature. We're developing it for somewhere between 4 and 77 Kelvin. The lower size and the level of integration is going to enable us to put quantum computing in same data centers in the same form factors that we use today for normal servers, rather than taking a 3 by 3 by 3 meters cube from IBM and paying maybe $15–20 million for it. Feel free to be shocked and stop me for questions at any time. There's really no way I can make this any simpler. So we are a chip company. Our unique technology, our patented technology, is something called a quantum transistor. It's a semiconductor device that plays within our quantum processor the same role a transistor plays in a classical. So it's really a basic building block that enables us to build a semiconductor, a processor device out of that, using that technology and making that on a single chip within semiconductor tools and technologies. The basic technology is based on solid state defects in diamond. and a photonic integrated circuit that switches photons around, does quantum processing in a photonic way. So it's not photons as qubits. The qubits are solid state spin qubits, but it's photon processing and photon switching to do the quantum processing, quantum measurement of the results. Once we are able to do that, and like I said, we're very young, we're very early stages in this technology, we will have better scalability, much better fidelity, and compactness, of course, when you're looking at a chip. This will enable the market to blow up with the size and price. We're basically trying to do the same transition classical computer did from mainframes to PCs, just enable that transition for the quantum world. So in terms of performance, we all know that there's been a race of how many qubits do I have? Do I have 50 qubits? Do I have 100 qubits? IBM just put out 400 qubits. Qubits are not all the same. Okay, qubits come in many different shapes and forms, in many different underlying physics in the hardware, and you have to talk about basic numbers to be able to compare them. This is the only graphical explanation I could put in that short of a time. It shows you how many operations you can do on a qubit before it loses coherence, but it also shows you how reliable those operations are. So if you're looking at the yellow and purple dots, they're giving you single qubit and 2-qubit gate fidelity. And if you're looking at on the other scale, you'll see how many operations you can do. And most of the underlying technologies today are on this map. This is where we expect to be. Obviously, at least as good as what's out there today, but probably better in some senses. Now, a lot of people are going to ask at this point, so why are you going to be better than somebody who cools a superconducting qubit to 15 millikelvins, or why are you going to be better than somebody who has ion traps in the vacuum tube? Basically, what provides media isolation and let's call it noise resistance is that I am inside the matrix of a diamond. My qubit is buried inside the matrix of very strong carbon connections. It's hiding inside there. So a lot of noise doesn't come into the diamond this far, and being able to communicate and control that qubit while it's in the diamond is where our technology is. So what have we done so far? Basically, to get the initial funding for such a crazy idea, we had to build a single qubit and be able to measure it. And we've done those tests at room temperature because cryosystems cost a lot of money. And we've been able to show 5.9 fidelity for a single qubit while you're doing every operation that you need to do on it at room temperature. So this got us some attention. We've been able to show that we can tune those qubits into an optic system that will be able to match and process that information. And we've been able to show that we will be able to scale those systems. We've also had some successful ideas and some patents around how we are doing the photonic processing within the PIC, photonic integrated circuit. And this has basically helped us raise the seed funding of $15 million right now. So this is our founding team. I've been in the startup business for about 30 years now. Startup in the IDF intelligence unit, and then did some R&D for 10 years, some sales and marketing for 10 years, and actually run a small fund, kind of a single LP fund for about 10 years, and decided to come back into the business of being a founder this round. My two partners, Dr. Torjuman and Dr. Bain, are both physics PhDs, did their PhD, I think 15 years ago together in the Technion in Israel, and then went to MIT, a little bit into Harvard, some Columbia University. Yigal has been doing silicon photonics for the past 10 years for Cisco, for Apple, for Google X. He's in charge of designing and tape outing our silicon photonics chip, the backbone of our chip. Moshe is an expert in solid-state physics and diamond physics, and he's the guy who came up with the idea of how to build a quantum transistor, how to build a qubit inside a diamond matrix and still be able to control it using CMOS. So the phase 0 was where we were working out of a garage, building our single qubits, testing them, and getting our stuff ready for funding. And our funding came in at $15 million in December 22. Actually landed in the bank in January. So right now we're like 5 months into it. We are now in phase 1. We're going to be using a budget of $22 million in 3 years to build the first POC chip. That POC chip needs to have any number of qubits in double digits. It could be 10, it could be 20, it could be 30. It doesn't really matter, as long as we can show that there's no compounding scalability problem. That as many qubits as I put on that chip, they're not going to interfere with each other's performance. This is not true of any underlying physics technology that is, interested in quantum computing today. Not in semiconductor, or not in not in ion traps, not in cold atoms, not in any of those guys. All of them, when you try to push them, into higher qubits, you get more error rates, and then you have to go back and invest in error correction, and that gets you back into the fact that you have the same amount of logical qubits as you had in a lower density. If we can show that that compounding scalability problem doesn't exist in our technology, which is what we assume, this is what we've looked at, then definitely we're going to be able to get the funding to build a scale-up chip. And about 3 years from now, I expect to be raising, if I did my job well in phase 1, I expect to be raising about $100 million to build the first scale-up chip. I'm not sure today how many qubits we're going to put in the first scale-up chip, but as many as it would take to get sales, basically. Because the number of qubits really isn't limited within our technology. It's not limited by our ability to manufacture or by anything else other than risk. So if IBM has 2,000, I'm going to be shooting for 3,000. Simple as that. This is a list of our investors for the 15 million round that we have already done. And I'm sure the next question is going to be, so what are you looking for? Basically, at this stage, I have money for 2 years, and the guys can work. And what I'm looking for is to complement my money for the 3rd year for the rest of the 22 that I need. And I'm also looking for strategic partners, people that can not just put in the money, but can actually improve the company's success chances. Okay, this is a very risky technology project. It's a huge market. And the more people, the more power I can bring into the equation, the better the chances of success are going to be. That's it from my presentation, and happily take any questions, sorry.
That was really interesting. I'm excited for it. The room temperature quantum computing. But Rajesh, go right ahead.
Hi, can you guys hear me okay?
Yeah, sure.
Just want to understand, in your proof of concept single qubit, how did you fabricate the actual diamond matrix? Is that process scalable to the extent that you know today? Then you want to scale
That's actually a very good question. So today there are several providers of, let's say, raw material quantum grade diamond plates, and there are not that many. Okay, we're working with a market leader. I'm sure you know it's Element 6, and they're providing us with quantum grade, couple millimeters on couple millimeters plate. Now the qubit itself is microns on microns, right? It's like 3 microns on 5 microns. So when we are going to process it, we're processing it with multiple semiconductor standard ways. So we're going into a fab, okay? And in our case, we went into university fab. We paid for using their fab for a couple of days. And the problem with that environment is that it's very contaminated. So there's a lot of risk of cross-contamination when you're trying to fabricate something, that's very clean, that's very specific, it's very pure. But we've been able to do, we did 10 prototypes, and 3 of them were clean enough to function, right? While we're doing what we're doing right now, we're actually building our own in-house diamond fab. We're buying the machines, we're doing all of that. Our budget is $22 million because about half of that is CapEx. And half the CapEx goes into building a diamond fab locally in our facility, and the other half is into a quantum optics lab, because when you want to test those kind of things, you need the right equipment and everything else. So the process is ongoing. While we're building our own facilities, we're still working with the, let's say, academic equipment, but it's not ideal. It's not going to give us what we need to push all the way to the POC. Does that answer your question?
It does partly, but we can continue afterwards, offline.
Sure. We are, by the way, already in contact and applied.
Perfect. Tim, you're up.
Yeah, thanks. I guess I have 2 questions. One of them you answered about the raw materials, but what is the TRL that you're at right now? So like where on a scale of maturity are you? And do you guys have any grants or non-dilutive funding that you've received that maybe are indications of product market fit from a government perspective?
All right, first, I'll remind again that we're 4 months into this, right? So it takes longer than 4 months to apply to a government grant, definitely in the US. We are working, by the way, with Eagle Point, who presented at the beginning. So we're starting to write down some applications for some US grants. but we haven't won any of them yet. And it's something I want to happen, but right now my priority is building my infrastructure because I have, $15 million sitting in the bank and I need to get the train going. I guess I'll put more resources into applying for grants once I feel everything is already ticking. The chief scientist here in Israel is very supportive of, let's say, high risk technology efforts, early stage. So we are working with the chief scientist. We expect probably next month to get some understanding of our funding participation for the first year. But other than that, I don't think I'm going to do a whole lot of more of that. The money is there for that kind of effort if people believe it might work.
Perfect. Perfect. Thank you. Thank you so much, Shmuel.
Sure.
Feel free to leave your contact information in the chat, or whatever.
They can get it from you, from Ben, and anybody who wants to talk to me. I'll be around.
Exactly. Okay, so I'll leave my contact information in the chat, and if anyone wants to reach out, feel free, and I'll filter it through. Perfect. But thank you so much. That was great. So we continue on to the next presentation. Next up is Bot Factory. I think I saw Carlos. Yeah, Carlos. Perfect. And presenting for Bot Factory will be Carlos. We can see your screen, but it's not full screen yet.
All right. Hello, everyone. Let me click the magic button to get us on our way. Okay, here we go.
Perfect.
So, hello. This is Carlos from Bot Factory. I want to introduce you to a company that is working on additive technologies to produce printed circuit boards and fabricate electronics in place with low resources, much less footprint on the environment. That has been around for around 8 years and is doing some leaps on different fronts. What is the problem? Well, we began by taking a magnifying glass to the PCB manufacturing industry, understanding how capital intensive it is. It requires lots of machinery, lots of space, chemicals, people. A lot of the processes could be or need a lot of actual hands to move them along the pretty different processes and quality control. And because of the way this process works, the lead times are very long, just to make sure that they optimize the capacity of each of their machines. There's an additional condition right now, which is in the US particularly, there's an increasing demand for PC manufacturing in the country because there's a push from the government to reduce the dependency on external countries like China or Mexico. So the way we are doing this, or what we're trying to do to approach this problem, is by proposing our own manufacturing method, right? And this is the easiest way to explain it. We are taking a full room of machines and we're trying to shrink it into a desktop-sized machine. And well, I guess the question is, does it work, right? Well, here's how it works. We have an onboard computer that processes all the input data. We extrapolate information that is critical for the manufacturing process, like where are the conductive traces, what are the sizes, where do you need shrinkage, where do you have insulations, where do you need connections between the different layers, right? What are the capacities that we can provide compared to what you're asking from, and being able to tell you, yes, this will look like this, or we will not be able to do it unless you modify it in this manner. Right? So it's a very proactive approach into manufacturing using additive. Then we use two materials, one insulating material and one conductive material to produce the interconnections of a PCB. So what you're seeing on the first slide where the head is moving left and right, that is where it's printing the conductive and the insulating material. And at this point, we have what you would usually see if you break like your cell phone. I'm pretty sure you're not going to do it, but if you were to open it, right, you will see like this green board or probably amber colored board with a bunch of components on top. So at this point, we have like that interconnection layer, which is called the PCB. And then our technology is also capable of extruding glue or solder paste into all the connection points where you're going to place the components. And then the next step is a head that will pick up all the components and place them in the right position. our machine has an integrated process. So when we calculated where we're going to print, we know where the pads are, and we know what the sizes of the components are going to be. We also know what could be the correction that we need to apply in terms of rotation and offset due to different factors. Like when you pick up something with vacuum, the part may be offset due to particles on the top, or even a gust of wind. So we have a vision system that corrects. And then what you get is what you see on the left side. It's a fully populated board, and the whole process beginning to end will take around 4 hours, right? So this is the machine that we have been selling for the last 5 years. It has evolved in many ways. It is more precise, it's faster, it's more compact, it's more reliable. And it's capable of helping labs and small prototyping houses create these or run these boards faster, to accelerating essentially their development process. Now, we are faced with something that's interesting for us. One, we have a good set of patents that we have built through the years. I'm not going to read what all these patents are. If you look for the name of the company, you will find it in a patent search. But the interesting thing is that we already have notifications from the US Patent Office telling us that HP tried to step on one of our patents, that Nano tried to step in a couple of our patents. So we already know that we are on the way of some of the possible large competitors that we could find on our path. This also gave us additional realizations, right? And it's the fact that we're at the point where the process is stable enough that we start wondering if there is something else we could do besides just prototyping. So this led us to work a little bit with the Air Force. The 402 EMXG is an operating function in the Robbins Air Force Base, which is in charge of creating boards to replace call it old aircrafts, right? So planes or helicopters or aircrafts that have electronics that are no longer produced, and they have to figure out how to reverse engineer them, repair them, and put them in action again. So time for them is critical. They also operate a large facility where they have all these manufacturing processes required for the traditional manufacturing of PCBs. They have faced 5 fires in the last 2 years because chemicals are very, very reactive. It's very hard to control. The training, keeping up with all the people is very hard. So particularly if you're trying to do small runs, they're not trying to produce millions of boards, they're trying to produce low runs. It becomes critical to find an alternative that is sustainable in time and is effective. A similar situation we found with Airbus, where they wanted to create like these cabins for their planes to essentially facilitate sales operation by customization. And in those cases, they also wanted to have something very quick. So these are 2 real examples of places where manufacturing of low volume is primordial to the continuation of the business, right? And bringing up new technology is it pays for itself. The ROI is very easy to explain. So where are we going right now? Or where we are and where are we going? So right now we're focusing our attention in what we call low volume PCB manufacturing. I'm gonna throw some numbers to give you an idea. The total value of 3D printing, and I'm talking about 3D printing of plastics, right? So we're talking about FDM and SLA, right? Worldwide, it's estimated at around $20 billion, okay? The value of PCB manufacturing is estimated at $90 billion. Did I say billion? On the 20th, 20 billion. PCBs is 90 billion. In the US, $22 billion is the size of the market for PCBs. But if you magnify that market and you look at how many orders are placed under 100 units, which is considered a low volume order, you will find that $6.4 billion per year are ordered in these low volume orders. Now, those small orders are usually not very profitable for manufacturers. And those are the orders that are going to hurt the most. Those are the orders that are usually sent outside so that the cost of manufacturing is sustainable and can produce some margin. But that is essentially going slightly away. So what we're doing is we're trying to approach contract manufacturers to take some of that load on the low volume, the type of production they don't want to do, and we want to do it for them. We can give them some additional advantages. For example, because we don't have the problem with the queuing, chemical management, the steps that they have to do, which usually is like between 27 to 32 steps that are very manual in QA and whatnot. We can offer things like next day shipping. Right?
Carlos, we should start wrapping it up.
Yes, I'm 2 slides from it, very close. So that's our first stage. That's where we are today. The next step we're going for is component manufacturing. So now that we know we're building your board, now that we know how to assemble your board, we can also tell you which of the components we can actually print additively. I'm talking about resistors, capacitors, and inductors. Those usually compose around 60% of the volume of your BOM, or your bill of materials. So that's meaningful. We have a strong effort going with the Space Force and NASA in manufacturing in space. This also affects oil rigs and other partners that we have that manufacture remotely. And lastly, we have the optical application where we can embed fibers next to copper traces to interconnect photonic circuits. We are in conversation with different entities that are developing these technologies and that they will need a way to solve this problem. Why now? I mentioned that US is pushing for this. We are seeing a big wind blowing in our sails. The market is growing. And we know that with quantum computing coming, photonics coming, space applications, and AI, everything is going to need a push towards more electronics, more manufacturing. And this simplifies a lot of the process. What do we need? Well, we are looking for investment right now. We're in our fundraise for 2.5 million. We intend to apply for a TAC-5 Stratify to see if we can double that via 1:1 matching. We are involved in several grants right now with the government. And if you know someone who is interested in additive manufacturing of electronics, we will also love to engage in a conversation and see where we can take this to. And thank you. I think that's pretty much it.
Ed.
Yeah, so I'd like to know, are you still restricted to only simple two-layer boards? Or can you do
Very good question. Our technology, the one that we're offering to our customers, is limited at 4 layers. We're actually a multi-layer facility. The new system that we're working with the Air Force is actually limited to 16 layers. But the limitation is mostly because we haven't validated extending it further. The process is very similar as you scale.
So you're doing drilling, like how are you doing holes, drilling and coating and buried vias? That's a bit.
Absolutely, yeah. So the way that it works is because it's additive. We place the first layer, and you can imagine we probably leave holes where you're going to have a via, and then we come back with the conductive material and we create the plating as we build upwards. So we can create vias, buried vias, blind vias, or all sorts of vias by just leaving holes and then filling them up with conductive material as we go upwards.
Okay, and what kind of your material are you using? Something with similar are you using copper, or is your conductivity equivalent to copper?
We're using silver, and the conductivity is like lower than copper. Then I would call it bulk copper. That's the main difference. So the type of applications where we are not very well suited is if you're going for high power management, then we're probably not your best option. But we have tested the technology in high frequency applications up to 6 gigahertz. It works fairly well. And it's repeatable, right? So when you print things, you know what to expect from them. And that's why most engineers can work with it without a problem.
So just in the end, are you able, like with these limitations, are you able to get into any products that will last, or it's only for prototypes?
Yeah, so that would last. So that's the other thing that makes us very hopeful, right? And what actually drives us. For a long time, we have been in this niche of prototyping because we felt this was the logic place for a machine of this sort. But we have learned from our customers that are actually using our products in their products that these boards are much more durable, because we actually, when we print them, we actually coat them in the end with some more insulating. So it's like as if you had it all put inside of a plastic wrapping. And the other thing that happens is that electronics are usually not meant to be structural. So you usually have a chassis around the board. So even if they are slightly more fragile than PCB, like the normal FR4, these boards are not meant to be the structure of your device. So most customers have not had an issue with it. I mean, actually, I haven't heard anyone having an issue with it.
Okay, thank you.
Mm-hmm.
Yes, just a quick two questions here. So one technical question, one business question. So do you have like a tolerance on a range for your PCB pad size that you deal with?
The what size? Can you repeat that, please?
PCB pad size.
Ah, sure. So the minimum feature that we're working commercially is 200 microns with 200 microns clearance. That's 8 mils to 8 mils, right? We are working on an experimental head that is 6 mils by 6 mils, and we can see how that keeps scaling because the heads are getting much better. We were using inkjet technology.
You said, do you have any customer currently or not?
Yes, we have sold around $5 million of products, and we have developed close to $4 million in projects with different types of entities between like government and private entities.
Oh, they're US companies or US customers? US customers? Okay.
But we actually sell all over the world. So we have some customers outside of the US as well. Yeah.
Okay, thank you. All right.
Perfect. Thank you.
For any other info you'd like to leave. And the next and last presentation of the session is Neologic. Avi, you're up. Feel free to share your screen whenever you're ready. I think you're muted, Avi.
Yes, now I'm not. Okay, hold on. Okay. Do you see my?
Yeah, it's just not in presentation mode yet.
Hold on. Okay.
Perfect.
So, good evening from Tel Aviv, or the vicinity of Tel Aviv. Neologic is located in Israel. We are operating about roughly across 2 years now. Our team, or our core team, has more than 100 years of experience. You can scan, the logos there with your eyes. We come from various industries, and we have the entire book of knowledge of chip design from what is called RTL to GDS2 through the fabrication process. I myself come from, I'm a device physicist, and I come from the foundry or the fab, and my partner, Ziv Leshem, comes from the design and VLSI design, and the rest of the team as well. And what we are doing is designing and plan to launch data center processors. This is my wow slide. So this is a small processor from ARM, and I will elaborate what we have with ARM in the sequel. Anyway, this is a very small processor that can be found in a variety of verticals, from the automotive, industrial, sensors, wireless, and consumer. And you can see in pink the realization of this chip. Doesn't matter the numbers, basically. What is unique about Neologic is that we are unlike any other chip design company that gets their building blocks from the foundry and design its chip. We have our own proprietary technology for designing chip. And with that, these are the types of numbers that we can deliver to any chip design. Even if it's your own chip, I mean, as long as it's, not quantum computing, but standard CMOS, and not necessarily limited to standard CMOS, but I'm referring to standard CMOS. Any compute, we can save roughly 25% of the area and 16% or 1/6 of the power. And in today's environment, in advanced technology nodes, this is overwhelming. Usually you get few percentage of performance improvement. In our industry, it's called a power performance area. And usually this product, you get roughly 2%. So we can give tens of percents improvement at any technology node and for any chip design. So we are future-proof and we are design-proof in a sense. The problems that we address, the top two are well-known, covered by the media. AI, ChatGPT is a nightmare for data centers. It really is an excessive overload on the computation power, as well as, of course, the facilities power resources. So we can mitigate. We cannot solve. Nobody can solve really, but we can extremely mitigate some of this problem. Moore's law is dead. NVIDIA CEO declared that a few months ago. And there is another hidden issue that most people that are not in the industry are not aware of, is that the rising costs of switching from one technology node to a more advanced ones are exponentially prohibitive. So the industry is basically stuck here around 16 to 28 nanometers. If you want to talk about 3 nanometers, there is only one foundry in the world today that delivers this technology in a pilot production. It's TSMC, and there is only one customer in the world that buys this production. Roughly 90% of it goes to Apple. So we can give or enable a company that designs its chips in 16 or 20 nanometer get effectively the benefits in the PPA of 2 generations or even up to 3 generations ahead. Namely, they can design the chips. This is the transistor sizes. So if they can design a chip in a 20 nanometer transistor technology and get the benefits of 10 nanometers technology without switching to the 10 nanometer. At the cell level, we have, as I said, we have a proprietary technology that at the cell level, if you are familiar with that, the chip design is basically like using Lego blocks to build something. So at the standard cell level, which is by the name, as the name implies, we can deliver for each standard cells of NeoLogic in comparison to the CMOS or the current paradigm equivalent, up to 50% power reduction and up to 40% reduced area. And this, if you see here, this is what Intel CEO told his executive last year, that when Intel will move 3 generations ahead, they will improve the PPA by 18%. That is roughly, on the average, 6% per generation. We can deliver, as you saw, roughly 60% per generation. That is 10 times more, okay? This one is effectively 60%. So at the cell level, we have a multiple of, I'm talking for the VC guys among you, a multiple of 50x in the price performance. Although in real life, you've seen, it's only 10x or so. We have already taped out a chip, a test chip, and the ARM M3 that I've shown you is really a real product. That said, we don't focus on revenue generation. Although revenue is important, we focus on value generation, and I will explain that in the moment. The data center market, well, by Intel's estimates, it's 110 billion. We estimate it to be 40 billion because we slice it a little bit more delicately. And we in that sector or segment, we look only on the or are going to go for ARM architecture. But the entire TAM of the plain vanilla CPU processors for data centers is 40 billion. By the way, if you look at Ethernet switches, it's another 40 billion. So we have roughly $80 billion direct market TAM. And by the way, these processors are very expensive. The median price of a data center processor is roughly $2,000, but you can see the price range. This is a very lucrative market, and therefore it is highly packed. These are the incumbents. By the way, it wasn't always so. 5 years ago, we had Intel dominated the market, roughly 95% of market share. Since then, it lost roughly 30% of the market share, and it goes between all these guys. So we have the incumbents that you are all familiar with, but you probably know that even TikTok or YouTube already now develop their own server processors. So the market has gone huge fragmentation in the past 5 years, and this poses a huge opportunity for us. That said, by the way, we do only compute. We don't do memory. We don't do analog. But the entire compute market or potential is 400 billion. Of that, as I said, we target the server processor, so we slice it. It's only 1/10 of that. But for the next 2 years, we focus only on hardened cores. I will explain what that is, and that is a 7 billion market TAM. These are two different customers, because these end customers at the end game, say 4 years or 5 years from now, are basically box vendors that we intend to sell chips, silicon, and they will integrate that into their boxes, rack-mounted boxes. Currently, we talk to these guys, basically design and produce their own chips, and some of them even sell them to these guys. So we are currently focusing on delivering blocks, which are part of the full chips, because we are a relatively small company, to these guys. And that profit margins could easily exceed 50% at the 7 billion, and even at 38 billion, and even at a 400 billion TAM. Okay, I'm rubbing. So our end game is selling silicon processors, server processors. This will be in 4 years' time or so. Currently, we focus on selling hardened cores. Hardened cores are simply digital files that are ready for manufacturing. This is a new market that we create. It doesn't exist today. Okay, so what do you see here? We talk to tens of customers. As I told you, we can generate revenue, but we don't focus on revenue generation. We talk currently only with 4 selected customers. These are the top 3. Another one is less important. We expect in the next 2 months to sign an agreement, a strategic agreement, either with Cadence or with Intel, and we start a negotiation with ARM. Each one of these companies, if signed, will jump high, even skyrocket, not just the company valuation, but its exposure to the market. So, and this is different than these guys that are beneath the waves. You know, even some of the names are very, I would say, well known, such as NVIDIA, Amazon, AMD, and ST. We talk to them all, but we put them all because they are not of strategic importance to us. We have raised $8 million, and as a fair disclosure, Robert Evan here is one of our investors. Merck M Ventures, the CVC of Merck, has invested in the company. We are looking for raising our Series A round, at least $15 million, and the purpose is to deliver a more complicated or complex processor, which is 1 generation ahead of what is readily available in the industry. It will probably be, you know, some sort of an AI engine based on ARM design, by the way. We have a strategic partnership with ARM. And of course, to strengthen the engineering team and marketing and sales. We already recruited 1 marketing person that is in New York. We have 1 man on the ground in Arizona. And we are starting really to I would say, to boost things up. This is the story of Neologic, and we will be happy to consider, you know, investors to joining our journey.
Thank you so much, Avi. Rajesh, your hand's been up for a little bit. Go right ahead.
Hi, Avi. Thanks for the presentation. Just wanted to get some more clarity about your business model. So your business model sounds like it's an IP licensing model. You're selling it to Intel, you're going to license your IP core, and they're going to make the actual devices.
Well, eventually we'll sell processors.
Okay.
But unlike any other processor company, we have a technology. So we want to monetize it, and we want to get it deployed in the market before we launch our product.
Okay.
Because it's a radical innovation, there might be an issue of market adoption. So once we get to HP Enterprise, Dell, and these guys, and they will tell us, okay, it's a good processor, it's an outstanding performance, but you don't have the track record of AMD. But at that point in time, we will be able to say, the AI engine of Amazon deployed for 2 years is ours, for example.
Can you share a little bit more information about your actual innovation? I saw that the claims are quite impressive, but it'd be interesting to hear some details of how you accomplish the gains in area and the power improvements.
Design concept, what we do is we take the standard CMOS paradigm. Those of you who are not familiar with that, the CMOS paradigm is you design chips in boxes, in a sense, and each box, the CMOS paradigm introduced roughly in the beginning of the 80s. Each box do two things, two very important things. One is it's functional. You need, if it's functional, that is assigned to, say, adding two numbers, multiplication of two numbers, whatever. The other more important thing is that it is robust to noise and saves power. And that's very important, because if CMOS has carried us successfully to where we are at for the past 40 years, now we are blocked because we stopped shrinking transistor probably in 2015. So there is no progress anymore. What we are doing, we are taking this block and we are breaking it into two parts. One, we realize it's function logic. And we do that by using single transistor logic. Single transistor logic was dominating the industry before 82. We gain speed, we gain area, but we don't want to pay but single transistor logic is very non-efficient in terms of power consumption. So we want the power consumption of CMOS. So we had another block that takes care of that. So basically our design is a two blocks design instead of single one. Of course, eventually you need that your two blocks design will be transparent to the designer and that it will be more efficient than what you have. Because otherwise people would say it will be larger in area or more power consumptive, people will say, let's use the original block or cell. So that's roughly speaking, then for executive level, I would say design concept. People, by the way, have tried that and failed. So we do that, but people have failed because they've tried to replace CMOS. Once you understand that you can't replace CMOS, everybody that comes like me, that comes from the fab, we see that. So once you understand that you can't replace CMOS, you don't want to, you want to augment it. So if you're familiar with the standard cell library concept that you get from the fab, we get, say, roughly 1,000 cells, keep them. We add our own cells, non-existing, that nobody has, to these. And this is what allows it. And it's obviously it's a little bit more complicated, but that's I would say the secret sauce of it.
Okay, thank you.
You're welcome.
Yeah, feel free to leave your contact info for anyone who might have questions or want to be introduced. I think there is one question in the Q&A if you want to get to that. So that wraps it up, everyone.
No, this is not mine. Okay.
Oh, that's not yours. Okay.
This is the PCB via size and trace.
Oh, okay, got it. All right, I wasn't sure. But thank you everyone so much for joining. Thank you, Avi, for being the final presenter. And feel free to stay tuned for the next showcase, Aerospace and Defense, coming up in June 29th. We appreciate everyone's participation. Have a good rest of your day and a good evening for those presenting right out of Tel Aviv.
Thank you. Bye.
Thank you. Bye-bye.
Bye. See you later on.
See you later. Bye.